All right, so my name is Stratis Ioannidis, and I'm at Northeastern, but this is joint work with my former colleagues at Yahoo. So what I will be talking about is article traffic forecasting with ADMM. And just to motivate a little bit why we're looking at this problem, think that you're a content provider like CNN or New York Times, and you would like to predict the virality of a certain article on your homepage. So to begin with, you might have some trouble doing this because perhaps the best data to do such a prediction might be held by somebody like Facebook or Twitter, for example. But nevertheless, there is a lot of information that a content provider can try to infer by using some kind of a proxy of virality. And what would that be? Well, basically, you can look at the traffic that an article generates and break it down by provenance. So every time that you click on a link, the web server that basically is hosting this website learns not only that you clicked on that link and that you visited a website, but also which website was hosting this link. Okay? So this way, you can basically, if you're a content provider, you can monitor and keep track of the fact not just that your website is being visited, but also that the person visiting it came from Facebook or Twitter or searched for a particular topic and therefore ended up on this website. So what I'm showing you here is not actually an article about Taylor Swift's new album, but it is an actual article. And you can see that the traffic that this particular article received was broken down into social traffic and search traffic and so forth based on provenance. And you can see that there is basically a diurnal behavior. And apart from that, the article kind of peaks really early on. So if it becomes viral, it becomes viral very early on, and then sort of like the traffic kind of tapers out and disappears. Okay, so in this kind of setting, where we have such traffic information broken down by provenance, what we would like to do is observe the traffic up until some point, and the traffic that we are observing is multidimensional because there are multiple sources of where users might have come from, and then based on this, predict the traffic at the next time step. All right, so, and again, to motivate this can be used as a proxy of virality, as a proxy of how much people are sharing this article or how much people are blogging about it or talking about it. It's something that is directly measurable from the provider. You do not need to have a deal with Facebook or Twitter and so forth to sort of understand this metric of virality. And it can be used by a provider to do actionable decisions, like either promote the article further up on their website or decide to place some ads in this article and so forth. All right, so what are the challenges here? So if you try to do a traditional forecasting on such a time series, one problem that you will run into is that trying to regress some kind of, and we'll see this, trying to regress some kind of a model using only very few data points is not going to give you good predictions. And this is especially problematic in our case because if the article goes viral and if the article is popular, this is going to happen very, very early on. So it's exactly at the time when we need to make our decision, and exactly at the time when we need to make our prediction. This is exactly the time where it's difficult to make predictions with a traditional forecasting model. Okay? So to sort of circumvent this problem, what we would like to do is somehow incorporate beyond the trace of the traffic up until now, also additional features and auxiliary information that we might have about the article, such that, for example, it's an article about Taylor Swift, it's a music article, and it's about an album release. Okay, so somehow we would like to incorporate metadata in our decision process. And in particular, if we know that Taylor Swift is trending, use this information, because other articles about Taylor Swift are trending, use this information in order to improve our predictions. All right, so our contributions in this context are basically coming up with a framework to do this incorporation. So we will jointly train forecasting models among a large data set of traces. And this joint training will utilize common metadata about common features about these articles. This ends up being a very large optimization problem, and we are going to solve it in parallel using ADMM, and I'm going to talk a little bit about that. And finally, we evaluated a solution over a real data set, and we saw that we have a considerable improvement. So I'm going to talk about all these three things. Yes, please.
You provide some context as to why you're trying to do this?
You mean why Yahoo was trying to do this specific?
Why are you trying to predict virality? What are your false positives, false negatives? What are the implications in some context?
So you can think that this is, if you do know this, you can surface the article higher on a stream, for example. So that's, for example, one way that you could use this. Another thing that you could use this could be yet one more feature for the article, the predicted virality that you could use for some other classification task. Okay. Any other questions? All right, so let's try to make this a bit more precise. So like I said, we're looking at a multi-dimensional time series. At any point in time, our traffic is described by, let's say, P values, each one describing a different provenance. And the trace is basically a sequence of such vectors. Okay, again, it's a multi-dimensional time series. All right, so we have a history up and including time t. We denote this with a calligraphic y. And basically what we want to do is produce a prediction. So we're going to have a parametric model. How does that look like? Well, so basically we're going to make our prediction at time t plus 1. We're going to predict a vector based on the history up until time t, up to and including time t, using some kind of a model, some kind of a function. And this function is going to be parameterized by some parameters beta. Okay? So I'm leaving this kind of abstract because we're going to talk about, we did use a lot of different models in our evaluation. But just to give you a concrete example that this community might very well know, so this is an ARIMA model. Basically, we're assuming that the traffic at time t plus 1 is a linear combination of the traffic up to tau steps before. Okay? And in which case, the parameters of our model are these matrices beta tau that effectively transform the past traffic to the new traffic. So you can think of this as an example. This is not the only thing that we looked at. All right, so, okay, so how do you find these parameters? Well, typically what you would do is that you would fit beta to an existing trace, okay? So you would have some kind of a loss function, the loss function here being a square loss function, and you would try to find the beta such that the predictions, if you were using this model at any point in your trace up until now, is close to the actual trace that you observed. Okay, that's one way of learning beta. All right, so it should be obvious that this is, there are problems with this if you have a very short trace, if you have a trace that is a couple of minutes. Yes?
Why is that the right loss function? Okay, equally about all mistakes.
So you needn't use such a function, that is true. So that's what we used in most cases, I think apart from the ODE. But our framework is kind of generic. So you could apply something else rather than what I'm plugging in here. All right, and so again, this is not good for early predictions. If you have a very small trace, you won't be able to make predictions. And moreover, the way that I've stated it right now, I'm not really using metadata that I might have about my trace. Okay, so how are we going to plug in metadata? Well, the approach that we used is that we basically regressed parameters from metadata. So what I mean by this, well, think that for every article, apart from the trace, we also have this auxiliary information. We have a feature vector that describes this article of, let's say, dimension m. And what we're going to do is that we're going to assume that the parameters of our model, so the parameters of the trace, are in fact a linear function of the features. Okay, so there's this matrix Z that maps features to model parameters. Okay, and then now the name of the game basically becomes figure out what this Z is. Okay, so basically over all possible traces that we have, all n traces that we have, we would like to minimize this loss function, whichever loss function you like best, subject to the constraint that the parameters that you're plugging into this model are a linear combination of the xi's, the features. And I can write this more concisely. I can just plug in the constraints inside the objective, and basically this is the objective that I'm trying to solve in terms of this matrix Z. And we also believe that not all features are relevant, so we're going to regularize and add an L1 penalty term to make sure that we get some kind of a sparse solution. Not all features are relevant. Okay? All right, so we can see from this that this indeed utilizes features and topicality. In particular, two articles that have same features, should roughly behave the same. They would have the same model parameters more or less. It improves on early prediction. We will also see this in practice because you don't really need a trace to regress the parameters. You can already extract them from the features. So, but one problem is that if you have lots of traces and you have lots of features and you have traces that last for a long time, this becomes a difficult problem to solve. It's a large problem involving many variables, as well as a very big objective that has many, many terms. Okay, so what we try to do in order to address this is that we try to solve this with ADMM. So if you have not seen this, I'm just going to describe this a little bit on a high level, but I just want to, don't worry about the math per se, but I just want you to get the intuition about how this works. So think that you take all the traces that you have and you split this data set across multiple machines. So each machine has some traces in your data set. And let IL be the articles in the ELF partition after you have done this partition. So basically, this is the objective that we're trying to solve. So we're going to rewrite it, and we're going to try basically to solve exactly the same problem, subject to a constraint that ZL is equal to Z. So all these ZL variables, where each ZL variable depends only on, interacts only with traces in each partition, all of them should be equal. So I have not really done anything here. I've just rewritten the problem by introducing these auxiliary variables. But the point here, and the intuition behind ADMM, it's somewhat more sophisticated than this, but the intuition is that the dual ascent of this problem admits a distributed implementation over all the machines. And to give you, I'll describe it in a bit more detail in a second, but just to get an intuition of how this works, basically there's this, each machine fits its own ZL to the data that it has, so it learns a mapping based on the data that it has. Then all these values are aggregated to a unique value Z, that is the result of an aggregation over these ZLs. And then this unique value, this consensus value Z, is sent back to the machines, and the machines fit again as ZL, but with an additional penalty that forces them to agree with a consensus. Okay, so rather than just fitting on your own data, you add a penalty that forces you to agree with a consensus. And if you keep doing this many, many times, you will converge to a global solution to your optimization problem. All right, again, so I'm going to go into a few details, but again, don't worry too much about it, just to get an intuition about how this works. So we have this global consensus value Z. This global consensus value Z is sent to the machines. The machines update some local dual variables through a simple linear transformation. And then, and this is the key step, so every machine finds a local Zi, okay, a Z1 or a Z2 and a Zk on their local data, along with an additional, so this is a local fit, but there's also a proximal penalty that forces, it includes Z, it also includes the dual variable, but it includes Z as well, and forces the ZLs to agree with a global consensus value. All right, so after this happens, the slaves, so these machines send back ZL plus UL to the master, and then the master basically sums these things up and computes an average, and then passes the result through a threshold function. So if you don't use a threshold function and you just average out, then you're basically computing the unregularized problem without an L1 penalty. If you have an L1 penalty, then you need to do this as well. So this shows up. Okay, so the point, so what is worth remembering about this is that there's a consensus value and that agreement is reached by forcing local fits along with a penalty that forces you towards the consensus. And if the function f is convex, and there's some additional assumptions that are relatively mild, then you're guaranteed that you are indeed computing a solution to your global optimization problem. So this thing will converge exactly where we want it to. And I want to point out that you can also parallelize the master. So here I had a master that I described it in a kind of like centralized way, but this is also something that you can parallelize and split among multiple machines, and the details are in the paper. Okay, so we implemented this using Spark, and in this implementation, both the master and the slaves are parallelized. So Yahoo was kind enough to also allow us to open source the code. This is basically a generic framework. So you don't need to use this just for time series solving. If you have any convex optimization problem that you want to add a penalty, an L1 penalty, and can parallelize it this way through consensus, you can use this code to solve it. And moreover, it's relatively modular. So All you need to specify is what is the local minimization plus penalty that you should be doing. You write code for that, and then our framework takes care of like partitioning the data and doing the ADMM steps and all that stuff. So it's up there, so feel free to use it. All right, so we looked at a data set that contained 3 types. So I think it was internal, social, and search. We had roughly 2,000 articles of about 14,000 features with 36 features per article. So like I said, the peak time shows up really early on, so in about 7 hours in this data set. And the mean duration of a trace is about 3 days, I guess. All right, so what we did is cross-validation. So we split the data set into pieces, and we tried to predict the traffic on the test set after we trained this matrix Z through our framework over the traces. And we're comparing here, we compared to more methods in the paper, but here I'm just going to talk about the naive, just fitting the parameters to that trace versus training beta from metadata, learning a Z, and then obtaining a beta through these things, and then trying to predict using that. And we tried a variety of different models, a lot of ARIMA models, a few ODE models, and a model that was specifically motivated from modeling functions like the ones that I showed you earlier on. So the take-home message from this is, first of all, ODEs perform much better than the rest of the models. But another thing to notice is that indeed the parameter model, the model where we use Z rather than fitting the trace, performs much better, precisely because it's not suffering from this cold start problem. And what I'm showing you here is two types of errors: one normalized by this variance, and one not normalized, at predicting the peak time traffic, at predicting how viral this article is going to be, in some sense. All right, so one more thing to show you. So basically, this shows the convergence of the algorithm when run over multiple machines, 50, 100, 200, and 400. So you can see that there's basically a speed up. So the more machines we have, the faster we converge. I want to point out that this is not immediately obvious, because although you're solving smaller problems on each machine, you also need to reach consensus. So you need more iterations to reach consensus, but you do buy out time because you're solving smaller problems. So even if you need more iterations, having more machines is better. All right, to conclude, we have seen that features can aid in forecasting. This leads to a large optimization problem, and we used ADMM to solve this. So this is a generic framework. It could be used to other forecasting problems that you guys might be interested in. And there are interesting questions here, for example, on how to optimally partition the data, because this also affects the convergence time. Thank you.
Hi, thanks for the talk. I have a question. So you replace beta with Z times X, but in the optimization problem, you can solve the beta directly, and then after you get the parameter beta, you can do a second step, which is separate from the ADMM procedure, because you know the beta value, and then you also know the X, which is feature, and I assume this feature doesn't really evolve over time. So then the Z value is just directly, you can get that from the second step, which has nothing to do with the first step, ADMM. Just wondering why you have...
Sorry, I'm not quite sure what you mean by a second step.
Because you're solving an optimization problem, and you're replacing beta with Z times X, right?
Right, but this optimization is solved once, so I wrote it as a constraint.
Yeah, so my question is why you have to do it all in one steps? Because my thinking, you can do it in 2 steps, where you solve beta first, and then you find the parameter Z. And the advantage of doing that is, for your approach, you need to store Z, which is P times Q, number of parameters. But then if you do in a 2-step approaches, you only need to store beta, which is has only P number of parameters, and where P is number of features, right?
I fully agree with you. This is definitely an approach that one could take. However, the solution that you would get this way would necessarily be worse than the solution that we're computing here, because the solution that we're computing here is over a space that spans these type of solutions as well. So if we're trying to minimize our loss, what we're trying to do and what we're doing will lead to a smaller loss than this approach. Though there are benefits, so you can think of this as an alternating method in some sense, okay, where you first optimize something beta and then you fit Z on that. And I did not try it, but it definitely leads to a higher error, training error. I don't know how it would perform on a test error. I'm guessing it would not be as good.
I'm not sure that it will actually get to lower training error, but I feel that.
We can talk about it offline. I can just one line. It's a one-line proof. It's very short. Yeah.
Thanks.
All right.
Any other question from the audience? I think let's thank the speaker one. Thanks, Stratis.